So now we're going to be looking at rotational kinematics. And these are basically using the kinematic equations that are for rotational motion. And they're almost all pretty much identical to the linear motion kinematic equations. So a lot of these are going to be very similar to just doing kinematics in one-dimensional motion. With the aid of a string, a gyroscope is accelerated from rest to 32 radians per second in 0.4 seconds. What is its angular acceleration? Well, angular acceleration, denoted by alpha, is the change in angular velocity in a given time. The angular velocity is, it went from 0 to 32. So 32 radians per second minus 0 radians per second. That's the change. And it took 0.4 seconds. And so that's, I don't know, like 80 radians per second squared. Let me just double check. Yeah, 80 radians per second squared. How many revolutions does it go through in the process? So this is sort of like some rotational problems we've done before, but revolutions, first, the way you think of it is you need to think of the number of angles that it is. So that's sort of like the displacement. So the change in angular position is omega naught t plus 1/2 alpha t squared. Okay, so this is just like the linear kinematic equation, this one. It's just now we're doing with the angular. So the initial is 0 because it started at rest. 1/2, the acceleration is 80 radians per second squared. And it went through 0.4 seconds squared like that. Okay, so it's 0.5 times 80 times 0.4 squared. And that's 6.4 radians. But this is the number of radians, not the number of revolutions. But you have to remember that for every 1 revolution, it takes 2 pi radians. Because 2 pi radians in my unit circle, right? 2 pi radians is going around the circle once. So I just simply divide this by 2 pi. I get about 1.02 revolutions. About 1. Suppose a piece of dust finds itself on a CD. If the spin rate of the CD is 500 RPMs, 500, then that's revolutions per minute, and the piece of dust is 0.43 centimeters from the center, what is the total distance traveled by the dust in 3 minutes? Ignore accelerations due to getting the CD rotating. Okay, so let's look at basically how many, so kind of a similar thing. I want to see how many radians that I sweep out over 3 minutes. So if I multiply this by 3 minutes, I know that I went through 1,500 revolutions. Okay, 1,500 revolutions, I multiply by 2 pi to get the number of radians. And so that's equal to 9,425 radians. And that is my angular position, change in angular position. But I kind of want to know the distance traveled. So actually, what you do to find the actual distance traveled, the equation is you use radius times delta theta times the angular position. The other way you could have done it is you say, well, if I go over 1,500 revolutions, I just multiply by the circumference. I'm going to do... You could have done as d is equal to 1,500 times the circumference, which is 2 pi r. And if you see this equation here, what I'm going to do, I did the 1,500 times 2 pi to get the angle, and then I'm going to multiply by r. So I'll do the same. I'll get the exact same thing. It's 4.3 centimeters times 9425 radians. And then divide by 100, turn it into meters. So I get about 405 meters. A gyroscope slows from its initial rate of 32 radians per second at a rate of 0.7 radians per second squared. So this is the initial angular velocity, and the acceleration is negative 0.7 radians per second squared because it's slowing down. How long does it take to come to rest? Well, so you could look at this equation. Omega final is omega naught plus alpha t, and I want to know when do I come to rest. So the t is going to be 32 divided by 0.07. 450. That's not 0.07, 0.7. I was going to say that sounded wrong. 45.7 seconds. How many revolutions does it make before stopping? Well, delta theta is equal to omega naught t plus 1/2 at squared. So the number of radians that it sweeps out is going to be 32 times 45.7 plus 1/2, oops, this has been alpha, 1/2 negative 0.7 times 45.7 squared. That's 731 radians. And then I simply divide this by 2 pi to get the number of revolutions, or multiply by 1 revolution per 2 pi radians. I get 116 revolutions. Okay. Thanks for watching. If you enjoyed this video, I go through a lot more of these exact kinds of problems with much longer videos on my website. It's entirely free. Check out the link in the description below.